Okay, in this video we're going to be talking about another type of confidence interval. This is a confidence interval for a population proportion, meaning the thing that we're trying to predict here isn't a mean anymore, but is rather the proportion of the population that falls into some given category. Maybe it's what percentage of people do we think plan to vote for a given candidate, or what percentage of people own dogs, something along those lines. Before we jump into it, we have a couple of things we need to cover. The first is there's going to be a little bit of new notation involved in this case. So let me go through that now. The value that we're going to be trying to predict, we're going to call P. This is the proportion of the population that we're trying to predict. So P is the proportion of the population that falls into whatever category that we're trying to predict. Voting for a given candidate, for example. X is going to be the number of individuals in the sample that fall into that same category. So X is the number of individuals in the sample that are in whatever that category of interest is. So let me modify both of these. Let me just say this is the P is the proportion of the population in that category of interest. And similarly, that's what X is as well. X is the number of individuals in the sample in the category of interest. N plays the role that it's always played. It's our sample size. And P with a little hat over it, this is going to be the symbol that we use for basically, it plays the same role that X bar played in the previous ones when we were trying to predict mu. P hat is going to be our guess for P. So it's equal to X divided by N, and it is the proportion of the sample in that same category of interest. So again, our goal is to be basically to compute P hat, use that as our first best guess for the true value of P. The procedure for one of these is similar to what we've done, but before we jump into the procedure, there's also a couple of sort of required assumptions or conditions that have to be met for this whole procedure to work. So let me just go over those real quickly as well. I'll call them our let's call them conditions. Maybe the requirements would be another good word. So the first is that the sample that we take needs to be a simple random sample. So I'm going to just scoot this down here a bit. So the first condition is we need a simple random sample. The second condition, and this one is one that's going to sound kind of familiar, it's, I'll come back to it in just a minute, the population must be 20 times bigger than the sample. This condition actually comes from the fact that this population that we're dealing with when we're trying to find the proportion, we're splitting the population into two groups, those that are in that category of interest and those that are not in the category of interest. And because of this, it winds up following some very similar conditions to a binomial distribution. So this second requirement is actually kind of a relic of that. If you remember when we talked about the binomial distribution, we said that when we're taking a sample from a population, even if we don't do replacement, it doesn't make that big of a difference as long as the sample is less than 5% of the population. Well, this phrasing right here, saying that the population must be 20 times larger than the sample, is equivalent to saying that the sample is less than 5% of the total population. So this is actually that same condition restated in a slightly different way, and it goes back to the fact that this thing is really following a binomial distribution. And so this next one, exactly the same thing, it's from the binomial distribution. We do have to have this population divided into only two categories. So in this case, right, you're either in the category of interest or you're out. There's no other options beyond that. This last condition says that our sample must contain at least 10 individuals in each category. Oops. There we go. What I mean by this is when we take our sample and look at the data that we have, at least 10 individuals have to be in the category of interest, and at least 10 individuals have to be outside of the category of interest. We'll check this when we actually do an example, probably in a different video. So we'll come and touch on those conditions. Now that we've got all of this settled, the next thing I want to talk about is the procedure. I mentioned earlier that it's really the same procedure that we've done in the other cases. Let me just highlight that fact here. It's the same 5-step process. So the first step is going to be computing or finding the point estimate. So the only difference here is that our point estimate isn't x bar anymore. So our point estimate, if you want to think about it this way, it's sort of if you had to guess one number for a confidence interval, this is the number you would guess. So going back up to our initial notation, we were trying to predict the true value of p. Our best guess is this p hat. So p is the proportion of the population, it's the thing we're trying to predict. P hat is the proportion in our sample. This is our best guess for this. So this plays the role of the point estimate in these problems. Let me go back and write that down. So in this case, instead of x bar, our point estimate is p hat, which is equal to x divided by n. The second step is, again, the same type of thing that we were doing before. We need to find the critical value. And the question in this case is, does this scenario wind up obeying the rules of a normal distribution or a t-distribution? Which distribution do we need to use? And it turns out that if you repeat the binomial experiment over and over and over again, you wind up getting a normal distribution. So this one follows a normal distribution. It's made up of a bunch of essentially like following a binomial random variable. As we repeat that experiment enough, eventually we get something that very closely follows a normal distribution. So that means in this case, we're going to use z sub alpha over 2. This is the exact same thing as we did in section 8.1. So we're going to be using a normal distribution and z instead of a t-distribution with t. The third step is to compute our standard error. The standard error is the standard deviation of our sampling distribution, which in this case is just a repeated binomial experiment over and over. So this will look a little bit familiar. This is going to be, again, a throwback to the binomial distribution. Our formula for this standard error is the following. It is p hat times 1 minus p hat whole thing divided by n, and then we take the square root of that whole thing. That's what the formula looks like. If you remember, for a binomial distribution, so let me just mention this here. Back when we did a binomial distribution, the standard deviation in that case, or sigma x, looked like np times 1 minus p whole thing square rooted. This is very similar. The difference is before we had to divide by n to get the standard error, so this was, the binomial distribution. We had to divide our sigma over the square root of n. We're doing essentially that exact same thing here. We're going from an n in the numerator, in the case of the binomial distribution, to the n showing up in the denominator, in the case of the standard error for that binomial distribution. So if that doesn't make any sense, don't worry about it. The point is, this is the formula that we're going to use, and it's tied to a relic of the binomial distribution. That's why it should look a little bit familiar. So I'm just going to erase this little piece over here. Don't need to worry about it. I don't want it confusing anybody. Let me move that piece out, and we'll come back to step number 4. Step number 4 is exactly the same as before. We need to compute the margin of error. And the way that we compute the margin of error is exactly the same as before. It is m, and it's just going to be the result of step 2 times step 3. So in this case, z sub alpha over 2 times that big square root of p hat times 1 minus p hat over n. So again, in words, all we're doing is taking the result of step 2 and multiplying by the result of step 3. The last step is also similar to what we did before. We are now going to compute, or construct rather, the full confidence interval. And that is just going to be, in this case, our point estimate, which is p hat plus or minus the m that we just found. So same idea as before. It's going to be our point estimate, which we found in step 1, plus or minus the result of step 4, which is our margin of error. And that is the procedure. In the next video that I post, we will do an example of this.